So I'm going to tell you a bit about what I've been doing the last 13 years, I think. So I'm overlapping with some of those waves. I've been navigating along those waves without actually realizing, because I'm coming from robotics. And I knew about self-adaptation, the initial work, but I was not really working in that community. So I developed some of those ideas in parallel with some connection, because I knew about some of the works. Actually, Radu Kalinescu was in the committee of my thesis. I only realized afterwards how relevant what he was doing was. My supervisor knew better, of course. So I'm going to talk you briefly about Metacontrol, which is about self-adaptive control architectures for autonomous robots. So I'm going to be merging all that we have seen today from systems engineering, how we model those systems, how we architect those systems, to how we use all that knowledge, all those models, for self-adaptation. So Elias was talking about architectural self-adaptation. So Metacontrol does architectural self-adaptation. He was talking about the MAPE-K loop. It also implements the MAPE-K loop. He was talking about the 3 layers architecture. It follows a 3-layer architecture. So I'm going to guide you a bit through all that. I'm going to skip quickly because Ivan already discussed the problem in autonomous robots, which is the architecture. But just for you to get an understanding of what's going on in robotics in the last 10 years, that was the time 15 years ago, I think, more or less, that ROS appeared. And all of a sudden, research that was being done in independent labs that were developing their own libraries, all of a sudden, everyone was able to start using each other's library because there was a common framework to connect things. And that was the part of the reason for the boom in robotics, basically. Because now, someone created a Kalman filter implementation, and other people were able to use it the next day, not after 3 months of trying to figure out how to rebuild those libraries, basically. So that was quite a change in robotics. And there was this promise that robots will be doing our dishes, exploring the ocean. We are still on that one, etc. So along the way, 8 years ago already, 7 years ago, we in Delft integrated one robotic system that won the Amazon Picking Challenge. So this was a more modest challenge about picking stuff from an Amazon warehouse. The system was quite complex. So this is similar to the collaborative robot that I presented before. Actually, that one was after this one. The one I presented this morning, that was developed by 2-3 people, PhD level, over a few months. To give you an idea of the complexity of this one, there were 14 people working on this in this system, plus all the ROS libraries that we were reusing, basically. So there was a lot of engineering effort in this system. So I think it's a more representative exemplar of an actual, more or less realistic. It's still a prototype, but it kind of worked 50% of the time, enough to win a competition. So you had 2 chances. One was really good, and we won. But along the way, Erdal yesterday already pointed out that there are quite some things missing. So when robots are facing really difficult situations for which they are not really prepared, or it's really complex, sometimes they just cannot cope with it and then just go to the floor. This was in the DARPA robotics challenge 7 years ago now, I think. Now we had the SAP, how you call it, the underground challenge. And with the SpotMe and stuff, robots are not failing that miserably. Also because now we move from bipedal robots to you need actually more points of contact to be stable and not fall, or if it falls, it doesn't look just that dramatic. But this is what's going on in robotics in the last decade, right? We are moving into more complex systems. Still, the challenging thing is to getting them to become products that we can trust and rely on because they will be working out of the lab. So the problem is the software architecture. One of the problems is the software architecture. So this is our system. This is 8 times or so faster. So it was picking objects, products out of an order. The robot did know in which bin the product was, but not exactly where, and there might be other objects interfering on the way, in the planning, etc. So it was, again, a simple pick-and-place application. Still, the architecture was really complex. This is not even the ROS nodes. The node graph I cannot depict here. That would be gigantic. So these are actually kind of functional components. This is not a proper description. It's more boxology. But just to give you an idea of all the methods that were being used, Super4 PCS to estimate the pose of the product based on the point cloud that was being detected. Of course, convolutional neural networks to identify the products, online planning, but also a database of trajectories that we knew were safe out of the bin because we know the environment out of the bin, etc. All that we have been discussing. Plus, in red, all exception cases that you normally have all the if this happened, just take this shortcut, right? So fallback mechanism, any application, even these ones, you have to manage extreme cases, right? So what's the problem here? The problem is that, as we discussed this morning, we are given a description of the mission, of the task of the robot. We go through design, all that we have been discussing this morning, how you decompose functionally, blah, blah, blah. You end up with a concrete architecture, a ROS node graph, that you expect that when put in execution, and this is the execution loop, you obtain a system behavior that is the one that you were expecting, that you designed for, right? So hopefully the robot was picking everything from the self. And you, to generate all this during design, you assume certain variability in the environment. That's why we use control theory to account for disturbances, that variability. But there are more sources, as Elias mentioned. There might be task variability, maybe the user now wants the robot to do something else, etc. So apart from so this knowledge that we have about the disturbances in the environment, etc., those become assumptions. Like we know, for example, that the robot has to pick the products from these bins. So that means that we use that knowledge, those assumptions, together with knowledge about architecting and engineering, tactics, heuristics, to decide what we were putting inside our architecture. So for example, a database of trajectories to reach the different bins, because the robot could have to do that anyway. So we could just use a database for those trajectories and adapt the final part of the trajectories inside the bin based on the runtime information. So based on the assumptions on the structure of the environment and our tactics, we created the architecture, right? So this worked very nicely. So we determine the components, the configuration of our architecture, and eventually we get a certain performance and a certain quality attributes of reliability and safety. But if our system is subject to more and more variability, uncertainty, we need to either keep increasing our architecture to cope with those, all right? With adding, for example, predefined alternatives. So we may have, and some people may be familiar here with feature modeling and in software to basically manage adding more features in your system, right? So predefined solutions, predefined parts of the architecture that can solve with those situations. So these are 4 different architectures for slightly different versions of the pick and place operation. So we had our Amazon Picking Challenge, we had our robot with 2 different versions of the architecture here. So in one was the one that I presented this morning, more predefined behavior, it will just stop and resume. In this one, it's actually moving to avoid the obstacle without stopping. This was using different methods, okay? So we had some commonality in the architecture, but actually different tactics for different things. So here we were kind of using just a state machine to control it. Here there was an entire online planning architecture for that functionality. So actually the functional architecture is quite similar at the high level, but there is some quite some difference the moment you go in detail on the different methods. So in that one, on the right top corner, people from Leuven, they were using actually learning to learn to pick objects, basically. So that's another type of adaptation. You can actually teach the robot. And it could adjust the learn trajectories based to the runtime information. So different architectural options that render a slightly different quality attributes, a slightly different functionality for a similar mission. So the problem is that in some cases we cannot bound that variability. And this, in underwater robots, that's going to be the case in many cases. So actually things go beyond what you expected regarding the environment. It might get too complex. You cannot predict how many people are going to interact with the system, when something is going to be an obstacle or not. So the moment you start increasing the boundaries, the moment you cannot cope by just adding more elements or more design at your architecture. So what happens, for example, if components start breaking? At some point you can just not anticipate and add another condition in your loops or in your coordination mechanism. This just doesn't scale with the variability. And the reason for this is that we have an open loop, and open loop of architecting the system. So we are closing a loop with environment, but with a fixed design. So the problem is that this is an open loop. If you are familiar with control, you know what happens with open loops. They work very nicely for a specific condition. The moment you have a perturbance, it will not work. So we need to somehow close the loop, and that's what the MAPE-K loop and self-adaptive systems are trying to do, close that loop so as to adjust the architecture as runtime. I'm going to skip this part, but only briefly. Ivano and Elias already pointed out to heuristics, tactics, things that, or closing the loop. So here are some, a very naive way of presenting some design assumptions that we did in our system. These are the design assumptions. Let me show you one example. We label those as levels of robot automation. I think Elias talked about levels of autonomy. So this is very related. We wrote a paper on that also, probably a different perspective on that. Just to give an example. So this is an adaptive system. This gripper is capable of picking certain objects given a very narrow boundary condition. So it actually can adapt to the object being in a slightly different positions. It's adaptive to a very, very small degree. We call it level zero because is what people in mechanics call compliance. So this gripper has some compliance, so there can be some variations that it can cope with, but very limited. So there is no feedback loop here. This is an example of what this gripper was capable of. So let me see which okay. So it's using this pinch element to pick that object, and it could only pick that object. Actually, we added that additional mechanism to the suction cap for only 2 products in here, but 2 products that most teams could not pick up because you could not apply vacuum to that mesh, basically. So that's why we put that. But also the dumbbell was too heavy for suction with this size of stuff. So we added one specific hardware feature. We call it level zero. So you just design your hardware to cope with that. There is no control, nothing. Level zero. We can have more complex mechanism. This is the next level. Is that okay? Based on what I perceive, I just take a selection of action, and this is the traditional sense plan act, or even very basic MAPE loop. Level 1. just sense once and decide, one shot. Level 2, this is, this one, sorry, that was selecting. This is a loop of sense, plan, act. You could start assimilating these to control heuristics, basically. So they can cope with different levels of variability. The more simple, the more limited the variability they can cope with. So this is not formalized, so this is a challenge how to formalize this, but this is actually one of my goals, to start putting a formal model of this and start reasoning on this. Level, I put the label 3 for feedback loops, PID control. And you can think of more levels if you start optimizing, if you start predicting, optimizing the future action costs, for example. You can use more predictive control and whatnot, and you can decide to call those next levels of automation. But the challenge, the real challenge, is actually to go beyond all that and to be able to adapt the architecture. I had a concrete example of all our design had one problem. So here you can see the point cloud that is being received from the camera when perceiving the beam. And the beam had metal frames. And I don't know if you are familiar with cameras, but metal frames with 3D cameras produce reflection. And actually, in our case, there was a gap. There was no gap in reality. There was a gap in the point cloud. So the planning decided that it could actually move the gripper through that hole. Of course, because for the system there was nothing there. What was wrong here was the assumption that the point cloud was correctly representing the environment, basically. So incorrect assumption that happens about the variability. We were not expecting this problem with the reflections. Actually, it was because of, if I remember correctly, windows, sun, daylight going in there, finding their way and messing up with our camera. Concrete architectural solution, actually, redundant information. We had information about the geometry of the beams. Why we were not using that? So we added a system to basically just add the collision model of the beams by default, basically, to complement this information. Another example of a problem, because we were only applying these levels of automation, so we had no way to understand how many products the robot had picked. In this case, 2 boxes that were too close, and our suction cup was big enough to capture both boxes at the same time, for example. So we need more adaptation, more awareness of what's going on. So problem is complexity, blah, blah, blah. We have discussed all this. And we can just not put more people designing the system. This does not scale, basically, because you cannot put boundaries on what an autonomous system in an unknown environment will encounter. So the solution is not to limit ourselves to these levels, but actually close what I call the level X, the mission loop, and just do MAPE-K, self-adaptive systems, adapt the architecture at runtime. And we need to have a set point, right? So what is our control reference for our adaptation loop? And that's why this is also goal-driven, is our requirements. That's what we want to accomplish. So we need architectural adaptation, but it needs to be goal-driven, driven by the requirements of the system. So that's Metacontrol. And I'm just going to mention what we are currently doing is just, for the moment, is limited to reconfiguration. So we have a set of components, and we decide which ones we deploy and with which configuration we deploy it based on architectural models that we obtain while we design the system using the ISE PPOA methodology. So we create this functional model of the system, we allocate the components, so we understand which components perform which functions. And our goal actually is not to maintain a set of components working. Our goal is to maintain the functions performing, because those are our requirements. So we don't care which components. We just need them, and we have information of which functions are performed or can be solved by which components. But also which quality attribute levels we can reach with which components. That's the model that we are using, the runtime model that we are using. So that we are doing a runtime, the runtime wave, the goal wave. And ideally, so theoretically all this is very nice, but if you have to yet create something else, that's a problem for developers. Typically they are very lazy. So it's like, now you are asking me not only to develop this, but to develop this other thing. So our goal is to try to automate this. So that's why we plan to reuse exactly the engineering models as they are, transform them into the runtime model, and have an reusable reconfiguration component, which is what we call the Metacontroller. That is completely reusable, domain independent. Or we can actually have modules for domains that we can add. And that's actually why we implement this runtime model in an ontology, so that it's easy to have general universal knowledge, which typically refers to general adaptation, general architectural concerns. But we can actually extend that easily with domain-specific knowledge. For example, if we are dealing with a robot that navigates, and we have knowledge about navigation algorithms that we can include in there. So that's basically what all I wanted to say. So I'm just, so we use ontologies. Before REMARO, people from a project on underwater robots came to me like, hey, we need some kind of supervisor system to deal with faults. Maybe we can use your Metacontrol. So we started applying it on an underwater robot. And we started to encode Metacontrol using ontological reasoning. So that's what we, together with Gustavo, with Julian in Oslo, we are now busy with, making this formalized. So right now, we don't use a probabilistic model. We use a description logic model in all, extended with SWIL rules, basically if and else rules. If you are knowledgeable, horned rules that encode basically architectural heuristics. And not even heuristics, just how the systems model work, meaning if a component that has a function allocated fails, then you expect the function not to be performed. So these kind of rules, that's what we encode as SWIL rules that allow us to diagnose the system, decide which components, what functions are being affected by components, etc. I think, so this is the model that Julian is actually now kind of formalizing. So I formulated this as a meta model called Thomasis, which is basically a simplified conceptual model for a system in which we have functions. And the difference with engineering models is that we take into account the runtime. So a function in runtime we call an objective. It's just an instantation. So the robot needs to be localized. That's a function. But at each moment, maybe you have a concrete performance required for that. So at one moment, you have the robot have the objective to be localized with this precision. It's similar to the class and the instance in object-oriented programming. Okay? But basically, these are concepts coming from systems engineering to represent the system and to be able to reason on the system. So this is basically our ontology right now. Originally, it was not coded as an ontology, but now it is, using the old language, plus the rules that allows us to add the adaptation rules on architectures. I'm just going to skip through it. I had an example with a mobile robot and adapting the localization function, basically. So if the robot cannot, if one of the sensors is failing, there is an alternative design using a different sensor plus additional components. So it will switch to that one. So that's the definition of the adaptation problem, and that's what we solve using reasoning. So this was actually 11 years ago now, a robot already with a ROS in there. So that was for my PhD thesis. By then, Metacontrol was implemented in Java. Now it's implemented in Python, plus the reasoning that this is in Java because we are using a reasoner of the self and a library. This was the robot in which this has been applied so far, the UNEXMIN in another European project. So just a concrete example, we had a very simple SysML model of the motion architecture. So you have propulsion that is actually providing the propulsion for controlling the motion. You have alternative controllers, a PID, a fuzzy controller. So the difference with what we saw this morning is that this morning we model one single architecture for the system. Here we have architectural variability. We have different options for that. And the whole point is how can we decide which option to use. So it's exactly what the MAPE loop is doing. Monitor was the state of the components, the propulsion, etc. Analyze, so what the state of this implies in terms of the requirements of the system. So if a thruster is failing, there is some lack of propulsion, the robot is not moving in the right way, it's not reaching its goal, then plan. So what needs to happen then? Do we plan an adaptation? Do we switch the propulsion system now? Do we reallocate thrusters, for example? So in practical terms, this is an example later developed in a journal paper. So we were adapting the beam matrix, that is the allocation of thrust for the control of the underwater robot. And the power of our Tomas's model is that you can model any subsystem this way because it provides general concepts. So you can model this also with that ontology and implement this adaptation. Certainly, you can implement this adaptation with another method. In the end, it's like control. You can just code one specific rule action to do. The challenge here was to create a reasoner for MAPE loops that you could translate. You could just reuse from one system to the other. You only need to write the model of the system that you want to adapt. And because we are lazy again, we don't want to write the adaptation model. We just want to take the model that the engineers building the system are writing down. So if they write it down in English, well, probably now we could also extract it with the current methods, but it's better if they use a formal model. Then we save a lot of NVIDIA GPUs running convolutional networks and transformers and whatnot to do natural language processing. So we do diagnostics, as I mentioned, just using the off-the-shelf reasoner for all language can be. So basically, querying the ontology. What Joris was mentioning this morning, they were doing with TypeDB is just ontological queries to do diagnosis, and then we apply reconfiguration, again checking on the model, actually not with the off-the-shelf reasoner, and this is something that we want to improve, and this improvement would be to just, I forgot the name. What's the query language for all? Sparkle. Someone? Sparkle. Yeah, Sparkle. There is some part that we have currently implemented in the Python code that we could generalize in some Sparkle queries, for example.
Carlos, can I ask something?
Of course.
Then, for example, there are still some PID controllers that might be switched in or out, right, as a component.
Yeah.
In your bigger system. So, okay, so basically, there is control, essentially, or adaptation at different levels, right?
Yeah, that's another very good point. So we are creating a manager for the control system. So we always assume that there is already a control system made up of PID controllers, planning systems, etc. Everything that is in your ROS graph implemented in there, so that we only take care of domain-independent adaptations. And that's why I was asking about this arrow that went from the environment directly into the managing system, because that makes the manager not reusable across domains. But actually we have the same problem, because to manage quality attributes are strongly domain dependent, how you measure them. So we have to measure also for Metacontrol directly from the environment for some things. But I don't want to, or I want to create an abstraction so that we can reuse the Metacontroller for any domain. So that's a current challenge.
I heard of a domain called metrology.
Sorry?
So I've heard of a domain called metrology, so basically the study of metrics.
Actually, that was my first lab at the university, was metrology. So I spent 3 hours measuring small blocks or marble blocks to measure the deviation of the measurements in physics, first year of university.
Can I have a small...
Yeah, this is already discussion. I mean, my presentation is just to discuss.
Would it mess up with some guarantees if you just start switching around controllers?
Of course, and that's something that we need to work on, is the transient state of the system, right? If you are just switching, and actually your controllers are creating outputs, and now all of a sudden you switch, but those signals should have continuity, right? For system.
Based on the fact that you have this single controller,
Yeah.
and yet, of course, some disturbance values, etc., but then all of this is out of the window if you change, and then probably offline you have to do all the possible analysis, and they're already pointing to some version here who will do it.
We have that bullet point in our research challenges in the group, right? The transient of adaptations as something that to work on.
It's something that will be so publishable, that seems. I mean, really, we need that.
Okay, note taken.
Calos?
Yeah.
So if you have, like, do I imagine correctly, your...
I forgot, sorry.
Yeah. So do I imagine correctly the way the system's supposed to work? So you have this database which contains the knowledge, and you map your functions, and you create, well, the blocks that are able to execute the functions, and to my understanding that those blocks which have more or less standardized interfaces that are able to be jump into your architecture's block. It works kind of nice when you think about, okay, I have a controller, I have a couple of execution modes, I can switch between those depending on the application. But if you have like a bigger system, is it like scalable? Because if you have reasonably complicated software architecture, something that you presented before, it took quite a lot of engineering effort from a person to actually design that before they even able to come up with interfaces and architectural decisions that are probably way, way hidden in that graph. Do you think that that's ever going to happen, that you're going to have a smart system that's able to create architectures like this?
Wow, so that's so for the moment we are basically selecting in between available. So we limit the scope of what we are modeling. So eventually, if we can manage to extract, to mine all that information and start creating abstract concepts of interfaces that can be reusable, but you understand what is in those interfaces, what is compatible or not, eventually yes, but I see the problem of, so the interfaces need to be really standardized. That's why if there is something like ROS, so you limit yourself to one framework that defines concrete message types, for example, then you can start matching these kind of things. People at Fraunhofer, they are working on these kind of models also, in which you can abstract the architecture of a ROS system, basically. But you depend on using standard types for interfaces, for example.
Yeah, I really don't see this being scalable yet.
And it's not yet. But the nice thing is that you don't need to model the entire system. You only need to model the part that you are interested in applying to make it reliable and to accept certain levels of variability, basically. So in a sense, this is a framework where you can plug in your research in self-adaptation, basically.
There is some research done by Alessandro Papadopoulos from Allard Tallinn, that's a professor there. Tries to build a system, a mathematical system
of a general, let's say, mathematical model of multiple controllers interacting from the control theory perspective. This is needed if you want to reach this. What you're saying is a valid concern. The way you're building complex systems, you make them more complex with all this stuff, right? Simply put.
Yeah.
So I think you need the abstraction. You need to not look into the boxes. Start not looking into the boxes, because the moment you start looking into the boxes, but to do that, you need your mathematics to be sound and kind of tell you that you can build on top. So you need to have hierarchical, let's say, control, which probably is something that already exists because everything kind of has been researched in control in one way or another. But you know, the general model of a software system that is being controlled in the general way, this is needed, you know, for building the abstractions and trusting the abstractions.
Can I try to answer your question and related to your comment, Elias, about abstractions, but just showing you the type of systems in which we have already deployed Metacontrol, exactly the same Metacontroller, exactly the same software repository. So together with Antwe over there and Heis, we implemented a first prototype of this at ABB with John Chengren there. So this robot is building a pyramid of blocks, right? So we implemented self-adaptation. Okay, what happens if one arm gets blocked? Can we implement this case with Metacontrol? So we did. So over a few weeks in summer, that's what professors do, have some fun actually doing some coding. So we implemented the first version of Metacontrol using ontological reasoning, and now the right arm has been blocked just because of touching it, so that there was a potential collision, and the robot uses a different configuration to build a pyramid with only one arm. It was a simple switch. Of course, the architectural alternative was predefined, but it was using the same reasoner, the same, again, the first prototype of Metacontrol, but most of the code is exactly the same done in these cases. So in this case, developed with Darko here also and a master student, we were estimating quality attributes, safety levels. There were other ones, but in this case, because of safety, next to an obstacle, the robot thinks, hey, I'm not using a safe enough navigation, so I'm going to switch to a different version of the dynamic window approach for the local planning that is safer, so keeps me farther from the obstacles. And again, the decision, the made case self-adaptation was implemented with Metacontrol, same code. We just switched the model of the system, again in all, describing the functional architecture. Instead of the robot picking and blah, 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 it was navigating, but same kind of model as input. Same code for reasoning, self-code for self-adaptation. Yet more, we decided to move into ROS2, and we were busy for a year with some people here in the MROS2 project, trying to abstract, create these layers so that we can reuse. So we integrated Metacontrol with mission coordination. So there is one thing, you need to configure your system to use the components to perform the plans, but actually there is always in a robotic system an upper layer deliberative creating the plan to achieve the goal of the robot. So we integrated it with that. We integrated it with ROS2, which actually provides for this self-reflection infrastructure with extended with system modes. So we could manipulate the state of nodes, which were kind of abstracting the physical architecture, concrete configuration of a component to perform a function, basically. So we actually integrated our Tomas's meta model at the functional level with a different model of components of physical architecture of the system. That was also another interesting benefit of our really, really abstract meta model, that you can connect it with other domain-specific languages as other models for your platform-specific, in this case, ROS2-specific system.
Carlos, can I ask a question?
Yeah, sure.
Yeah, sorry. It was a really nice video on the 3 blocks. I think it's a very good example on system reconfiguring itself. And a question I had is, how much reconfiguration actually happened there? Is that just like one block swap? Is it?
Yeah, it was two or three, because we also had, I saw that case, but another case was, it was also reconfiguring when the light conditions change. Then the robot was using some QR codes, so visual markers to position itself,
Yeah.
and it was also robust to light conditions, so it would switch the configuration of the camera. So we saw that even different elements, if you model that in your system, you could switch between both. There were two cases of adaptation that we implemented there.
So
with the
basically,
same.
inside the system, it would decide if there are certain capabilities are available and then
Exactly.
disable them and then do replanning.
Exactly,
Like that.
yeah.
Okay.
Yeah.
Really nice.
So again, same code now. We developed some tools. Darko created a language to define the architecture for this purpose. Again, you don't need to model everything. You only need to model what you need for your application. In this case, we were modeling at the skill level. But the fun thing is the video. It should be running together with Intelligent Robotics Lab at the University of Rey Juan Carlos. Let me speed up a bit. Again, the same. So 10 years afterwards, we were able to reproduce my thesis experiment, but on a different robot platform, which is a bit more advanced. And basically now with software that we are deploying in different robots. So again, I think reusability is one of the challenges, right? Not only, so the features were the same as 10 years before, but now we have something that we are porting month from month to one different robot without much effort anymore. So the system was using a laser to navigate, and at some point we decided that there is a failure or there is too much glass around and it's not reliable, so the system can switch to navigate with the camera. So it basically uses the camera as if it were a LiDAR scan. Yeah.
Very quick question. Do you have an automated step from... thanks.
Thank you.
Have you automated the step from SysML, if I understand the whole thing correctly, to the generation of rules? Or is it still manual?
So two answers. Theoretically, yes. In practice, it's not practical.
Okay, but
Because
it's
also no
possible.
one is using SysML that seriously to actually.
see.
So I actually had a nice exchange with Andre some years ago, because that was one thing that we decided, whether we were actually creating this transformation in between SysML and Tomasis and our ontology. And I actually, in practice, tried to create the variability model in SysML, and it was just a nightmare. So I had to create so many elements in the model to model something simple that we decided it was not really practical.
And then what is the practical approach? So how do people model variability in robotics?
So what we took is use domain-specific languages. So we designed our own little language so that architects could express what they needed adaptation for, so that they could write that architectural model for adaptation.
What about using these trees that were explained to us in the morning? I think that this could also be an option, right? So kind of extending the language of the trees.
That was SysML. Yeah,
That was already
that's it.
SysML.
Yeah. So
Also in the invited talk?
Yeah.
Okay, then fine.
And no. You mean, yeah, no, the invited talk, that was an ontology, but using TypeDB. So
Right.
that's basically what we are
Anyway.
doing now. We are writing the old model, which you can depict as a graph also. So actually, to simplify, we design a domain-specific language because it's still more simpler than writing the ontology or even this TypeDB thing, which is, again is writing a complex graph.
You mentioned this concept of skill. So in the past it was mostly like components, and now, at least to my experience, is like many people now in the last couple of years, they're like mentioning the concept of skill. So they're like, even from software perspective, but also from robotics. I mean, it's still some work in progress, but some people even came up with some kind of life cycle for skill even, which is not, I mean, not on a ROS level still, but yeah. So this is why we designed this language specifically. Yeah.
I was just pointing to some challenges that probably are very similar to what you pointed out before, how to optimize the reconfiguration. We are not really doing any cost estimation for that we should. We need to optimize only the plan and the system adaptation, so the behavior and and the structural adaptation, how to integrate the heuristics. So right now we are doing very simple reasoning on the architecture of the system. So allocation of functions to components, if something is broken, the other one is broken, but we are not reasoning about the heuristics being applied. So it would be very interesting if we can model those heuristics somehow, so that the system can reason, hey, now I need to be. So if we can answer this, so we have our robot there, and the robot says, hey, I need a more energy-saving controller, because now we have this this challenge energy, and I need to reduce my footprint, my CO2 footprint. So I need to be more efficient controlling my thrusters.
Can I ask a question, just to understand? Imagine I have two alternative controllers and I'm operational, so it's during the mission. Are the two controllers running already in parallel and then you switch?
That relates to the switching problem that we were discussing before. So right now not. We have still our systems are lab systems. And of course the first thing, especially with a robot that is moving, is like you cannot just swap your control immediately.
Okay.
And that's an interesting problem from a hybrid system modeling perspective. Because here we are taking some decisions at a level of abstraction, but actually there is a continuous discretized system that is running at a certain frequency that you cannot just swap like that. So we need to model that.
And also predict when you are about to switch. And then
exactly. So actually, forgot the name. There is forgot the name about selecting controllers on the fly. So you start running one next to the other one, and at some point you switch. And you can actually apply some reinforcement learning to start predicting what's going to happen to one or the other one, or actually adapt the control law to be something in between. So you have one, you start running the other one, and in the end you create your control law based on both that transitions from one to the other, basically.
That's difficult.
That's something that one of my PhDs is looking into.
In the previous slide, you mentioned about some challenges, including integrating with the neuro. I wanted to know that what is the reason the advantages of using the neuro or any knowledge system processor instead of the reasoner that you are working
So the idea here is that, so if we are going to be using engineering knowledge, it would be good to have all engineering knowledge and not just the one produced by a local development team. So for that, you need some cloud infrastructure where you are storing that, and that's one of the goals, not of NoRob, that is the platform, but the, how you call it, the is cloud knowledge for robots. So not only, to my understanding, for the moment they have a lot of execution traces related to manipulation. But it would be very interesting to start also capturing the design of those systems and be able to use information about the design. That's, for example, what Ivano showed us how to do scientifically mining those repositories. So it would be very interesting to start populating such a shared database of heuristics. And the idea is then we could actually query that and actually look for that controller that will save us some energy. I think we are not being recorded anymore.
Well, it's probably
it's
easier
over 5.
to hear me like this. I'm missing the option where Metacontrol fully synthesizes the system architecture. Instead of just selecting between, cast in stone alternatives, why? Let me be more lazy than I already am, right?
You want to lose a job because you
Exactly.
need the money.
Well, someone still needs to maintain this, right? So. No, but really, is that a challenge, or is that purposefully not on this list?
Is that it's purposely not on this list because this is a list of things that I think we could do even in a year if we are just onto it. That one would be 10 years. Something like the autonomous car, It's going to be in the next 10 years and probably will take 50, but we get there.
That's disappointing.
But that's a really good challenge. And this relates strongly, I think, with all this engineering knowledge that it's captured in heuristics. Heuristics means we still don't really know how to mathematize the creating that. So I'm actually not so sure that this can be done in the next 50 years, completely. Maybe, but I'm not sure we can reach all the level of abstract thinking and creativity. We have for
It's
these
supposed to be a
paintings.
challenge, right? So
Well,
if
actually,
you
right
already
now
knew
people
how
are
it would work,
generating
then-
pictures, right, of whatever. You can just tell the GP blah blah blah
Yeah, exactly.
to generate the
Generational
picture.
networks.
But the thing is, would you trust that picture to, for example, pilot the plane you are in? Something that
Well, I guess
something
that was
came up.
partly his comment earlier. I mean, basically, you have a very complex system that you designed, that you know works correctly, and for this to work, you would need to design 5 more, and also know that they all work correct, for instance.
Yeah.
And then you have a system that can switch between 5 different alternatives, but you would still need to maintain sort of correctness for all 5 of those alternatives. So I guess that was what your question was, right? Sort of.
Actually, sorry, I didn't even consider the generating of architecture being a challenge. I thought that system is able to do that.
No. This is for the moment it's selecting. So you model the alternatives.
Actually, why not? Because to my understanding, your system has rules.
Yeah.
Based on those rules, it can introduce one block or the other.
Yeah. So
Because then you need to do analysis of the control loop at runtime. Fine.
In a big
Yeah, but
picture,
it's
yes,
hard.
but actually what I was thinking in a most simple scenario, you have a certain architecture you design by hand. I'm saying that's fine, you design it by hand. Then you convert it into a set of rules which you put into your database.
yeah.
And if you run your inference engine on that database that you just constructed from your handcrafted architecture, it should spill it out back.
Yeah, and that's what it's doing. But then it's limited to the design that you made. So
Yes.
there are no additional
But if you-
designs or options.
If you introduce 5 different architectures into this database of yours, then it should create, in the specific condition, 1 out of 5 options.
Yeah,
But if your conditions are mixed, then it should produce an in-between versions as well.
actually, so it's not switching between 5 architectures because the alternatives can be at any function basically. So it can create all combinations basically based. So it depends on the granularity of the knowledge that you provided basically. That it
So
will
in principle,
speed,
it does that. It does generate a system at
Yeah.
runtime.
Yeah.
So
Yeah,
so my
but-
assumption was it does generate the system on runtime, but you're just not explainable.
It's not as free-form.
Yeah. It's
Theoretically, it's very free-form, but you didn't want to make very large models, which would require.
exactly.
So
Yeah.
if you introduce 10 different architectures, which each of them has individual rules, and then the rules are mixed, so even with the example where you have lighting conditions for cameras, and at the same time conditions for the hand, so you could have 4 different architectures because
Yeah,
you have
exactly.
4 different combinations, while you actually design only parts of them individually. So you would have not designed the system completely.
Yeah, exactly.
Providing the behavior of the system is only defined by the individual components and
Yeah.
not by the combination.
But
So-
it is
In other
designed.
words, if it's larger than some that's partial, and that's where you get into the predictability issues. I think that's
Yeah.
also why you limit the reconfiguration, right? You're able to afterwards actually explain why this particular combination is true.
Actually,
That's what I said. It's very hard to trust the system, but it's not limited at this point to do that.
no, the limit is the model. So for the moment we are using very simple models because we are lazy modelers and we haven't created a gigantic model with a lot of options for each function basically. But we can, we can reason and potentially model as big as you want the architectural options basically. So in that sense, the framework is not limited, except by the models that you write.
Yeah, exactly.
Yeah. Well, it's limited by the rules that we have included about the architecture, basically. So we haven't encoded rules for all types of quality attributes, for example. But we have some general rules about them, for example.
Yeah, so maybe the challenge is figuring out where is the limit of your model. How big can you make it and still
Oh, we have some experiments of what we can encode in an all ontology and still have runtime reasoning, and it's quite okay with the current SAT reasoners.
I think that there are two, from the point of view of engineering, are two levels. One level is the allocation of functionality, that is more simple, because the only rule is maintain the modularity. Reallocation of functionality to different physical components and maintaining the modularity properties. Another is quality attributes. Quality attributes are more complex because there are conflicts between quality attributes. As I was talking with Carlos, for example, security and safety and performance are in conflict. You can have a system with high level of security and high level of performance. You want, or you sacrifice performance or you sacrifice security. In some cases, they're naming soft goals. Soft because you cannot meet 100%. So dealing with tactics for quality attributes is more complex because you have conflicts. The first level is allocation, working only with functionality. And the great function in resilience, we talk about also functional degradation. In some cases, you run a system that is functionally not with all the functionality of the previous system, with partial functionality, but it works. So you have to deal with all these aspects, with all these concerns.
Yeah, just one more thing. I think one thing that we should maybe look into it, I think there was a hint towards this direction. It's about dependability, actually. I think the dependability between different subsystems. So this is how maybe we can make some constraints about the overall model. I think if we analyze some kind of dependability between different subsystems of different components, and then you can see which type of component configuration can go together with, maybe not all navigation configurations can go with all, let's say, localization or perception, let's say, depending on what you're, depending on what you're using. And I think this is a direction we haven't explored so far.
This is something that actually Joris, in the model he presented, he has modeled more in detail the functions, inputs and outputs. So they actually reason on, okay, can I use this component with this other one because the input of one is what the other one is expecting, basically. In that sense, we are only dealing with the functional decomposition, and they also have reasoning about the interfaces, basically. So they actually do this checking, constraining in the reasoning whether actually one component can work with the other. Yes, Sasan.
Is there any work related to the testing of these types of systems? Because I think the traditional approaches for testing might not be useful anymore when you introduce Metacontrol. So
I think Julianne tomorrow is going to talk a bit about her work on rewriting logic, modeling the adaptation loop that we implement with Metacontrol to test, basically to verify the expected behavior of it. But we also need to explore, we have done very, very simple tests with the ontological reasoning and mostly related to scalability, how this scales when you have a gigantic model. Is it still feasible to expect to query and have an adaptation loop closing at, I don't know, 1 second, 1 Earth or so?
The real-time testing, you need to basically inject fault and at the same time examine the combination of other architectures which come to play, yeah? So.
Yeah. We need to, that's why we are in REMARO. Exactly, work in progress. And actually work expected from other people.
So we have done some work in Oslo with a postdoc of mine on reflection in programming languages, and in particular semantic reflection, meaning the encoding of runtime state, lifting it into an ontology. And that allows us, in that case, to use query reasoning over semantic web to make kind of diff between the runtime state of the program and asset model that we are working with. And I think maybe something similar could be used for Metacontrol. So not just use the ontology to reason about the sensor data and the knowledge, but actually to lift the configuration of the Metacontrol also into the ontology and use ontological reasoning over the configuration of the Metacontroller.
Yeah.
So that could be something interesting to look into.
Definitely. So close the loop, close the self loop, basically.
And in particular, that allows you to have the formalization of the Metacontrol state in the same formalization as the domain knowledge. So you can actually talk about the two in the same queries, which is why we did it for the digital twin simulators.
Cool. I think,
who wants the microphone after me? I don't know if we are recorded or not anymore.
I think they were finishing at 5 with the recording, but I think closing the self loop is kind of a nice closure for the day. Unless there are more questions, comments, discussion, then we just close the day. Thank you very much. Close the day and the school, in a sense. So we have more private event tomorrow for the people in the REMARO project, but I would like to thank especially today to our speakers, for which please, if you come here, we have a small present for you. You don't know, or you are nearby. So some robotic, robotic theme.
Thank you.
And Jose Luis. Thank you very much for attending. Thank you very much to the participants not in the REMARO. I hope you enjoyed the event, you learned some things, and thank you very much to all our REMARO partners for coming, and see you tonight and tomorrow for more work on underwater robots. Thank you very much.